The coolest spot in the universe, presented by Science at NASA. Everyone knows that space is cold. In the vast gulf between stars and galaxies, the temperature of gaseous material routinely drops to 3 degrees Kelvin, or 454 degrees below 0 Fahrenheit. It's about to get even colder. NASA researchers are planning to create the coldest spot in the known universe, inside the International Space Station. We're going to study matter at temperatures far below anything found naturally, says Rob Thompson of NASA's Jet Propulsion Laboratory. He's the project scientist for NASA's Cold Atom Lab, an atomic refrigerator slated for launch to the space station in 2016. We aim to push effective temperatures down to 100 picokelvin. 100 picokelvin is just 1/10 billionth of a degree above absolute zero, where all the thermal activity of atoms theoretically stops. At such low temperatures, ordinary concepts of solid, liquid, and gas are no longer relevant. Atoms interacting just above the threshold of zero energy create new forms of matter that are essentially quantum. Quantum mechanics is a branch of physics that describes the bizarre rules of light and matter on atomic scales. In that realm, matter can be in two places at once. Objects behave as both particles and waves, and nothing is certain. The quantum world runs on probability. It is into this strange realm that researchers using the Cold Atom Lab will plunge. We'll begin, says Thompson, by studying Bose-Einstein condensates. In 1995, researchers discovered that if you took a few million rubidium atoms and cooled them near absolute zero, they would merge into a single wave of matter. The trick worked with sodium, too. In 2001, Eric Cornell of the National Institute of Standards and Technology and Carl Wyman of the University of Colorado shared the Nobel Prize with Wolfgang Ketterle of MIT for their independent discovery of these condensates, which Albert Einstein and Satyendra Bose had predicted in the early 20th century. If you create two BECs and put them together, they don't mix like an ordinary gas. Instead, they can interfere like waves. Thin, parallel layers of matter are separated by thin layers of empty space. An atom in one BEC can add itself to an atom in another BEC and produce no atom at all. The Cold Atom Lab will allow us to study these and other phenomena at perhaps the lowest temperatures ever, says Thompson. This could lead to the discovery of interesting and novel quantum phenomena. The space station is the best place to do this research. Microgravity allows researchers to cool materials to temperatures much colder than are possible on the ground, where the heavy pull of gravity can interfere with the process of refrigeration. No one knows where this fundamental research will lead. Even the practical applications listed by Thompson, quantum sensors, matter wave interferometers, and atomic lasers, just to name a few, sound like science fiction. We're entering the unknown, he says. Researchers like Thompson think of the Cold Atom Lab as a doorway into the quantum world. It's worth noting, however, that doors can swing both ways. If the temperature drops low enough, we'll be able to assemble atomic wave packets as wide as a human hair. That is, big enough for the human eye to see. A preacher of quantum physics will have entered the macroscopic world. And then the real excitement begins. For updates about the Cold Atom Lab as it news launch in 2016, stay tuned to science.nasa.gov.